Hi guys, I have a question to you. Are you entirely happy with the performance of your batteries in cell phones? For me, not. And what we use in our cell phones, it's usually lithium-ion batteries. They look in the following way. So these batteries consist of graphite acting as anode material and different oxides acting as cathode materials. These batteries are known for lightweight, high energy and power density, long life cycles, but suffer from aging, degradation of active materials, high cost, safety, and recyclability issues. So, what do we need to do? We need to search for new materials, more attractive as electrodes. Can we move from oxides and oxygen-containing compounds to the neighboring element, nitrogen, and nitrogen-containing compounds? Nitrogen is not only the most abundant gas in our atmosphere, but also forming a variety of different compounds. Today, we will focus only on nitrides and nitridometalates. So, nitrides are compounds consisting of nitrogen in oxidation state -3, which is bonded to different metals. These compounds are known for rather simple crystal structures, variety of chemical bonding from ionic, covalent to metallic, exceptional hardness and corrosion resistance. Therefore, we usually use them as different coatings. Nitridometalates also consist of nitrogen in oxidation state -3, which is bonded to different transition metals, forming together a nitridometalate anion, which is stabilized by different cations, alkali, alkaline earth, rare earth element. These compounds have extremely diverse crystal structures, complex chemical bonding, because they combine covalent and ionic bonding together. They possess diverse oxidation states of transition metals. The systems are extremely complex and have intriguing physical properties. But they are extremely air and moisture sensitive. It's challenging to synthesize and characterize, and therefore we don't know how to apply these materials. So the question is, can we use these challenging materials as electrodes in lithium-ion batteries? To answer this question, we have started with synthesis, and we used high-temperature centrifugation-aided filtration technique. We started with starting materials, binary nitrides, chromium, lithium, mix them together, put in tantalum crucibles, welded shut these crucibles, sealed in quartz tubes, place them in stainless steel containers, heated up the system to elevated temperatures, hold down, cool down to 300 degrees, and centrifuge them to separate crystals from the flux. As a result, we were able to synthesize nice crystals. So, now to the results what we obtained. We were able to grow black metallic crystals and obtain crystal structure which can be visualized in the following way. It's quite complex, but we will divide it into simpler parts. Firstly, trigonal, slightly pyramidal units of chromium, chromium N3. Secondly, slightly pyramidal lithium-nitrogen units, which form slabs along the C direction in the unit cells. To know if this compound can be used in batteries, we need to understand the oxidation state of chromium. For that, we measured magnetic susceptibility. From effective magnetic moment of 0.1, we established chromium-4 in this structure. To prove that, we also used vibrational spectroscopy. We measured our compound and two compounds as standards, where we know the oxidation state of chromium, and then from the shift to higher frequency from the standard compounds to our desired compounds, we proved that the compound has chromium-4. Okay, what else do we know to use these materials as batteries? We need to know the bonding in the compound. For that, we compute some calculations, and from QTM shapes of basins, we establish the bonding inside the compound. The interface between chromium and nitrogen is planar, which leads to covalent polar bonding in the compound, whereas the interface between lithium and chromium is more round, which leads to mostly ionic bonding. Moreover, we checked the conductivity of the compound, which leads to semiconducting behavior with a small band gap of 1.1 electron volt. So, why this is so important? Firstly, this compound has intermediate chromium oxidation state of 4, which can be beneficial for batteries. Secondly, we saw the slabs of lithium nitrogen units, which are not layers as in compounds which we use nowadays in batteries, but the slabs can be also beneficial for battery performance. The lithium-chromium ratio is 1:1. It's quite good, but usually we aim to higher lithium content in the cathode materials. Therefore, we performed other synthesis and were able to synthesize also black metallic crystals. When we obtain the crystal structure, it can be visualized in the following way. You immediately see that it's much more complex than the previous compound, right? We can also divide it into simpler parts. Firstly, chromium units. We saw it in previous case, a slightly pyramidal trigonal unit. But also this compound has a double tetrahedra, chromium 2 and 6 units. This combination of two different units in one compound is the first case in this family of compounds, and actually in nitride metalates, which was observed here. What happens with lithium? Firstly, we see again trigonal planar units of lithium, but also dumbbells and tetrahedra. So now, if we look mostly on lithium substructure, we will see this complex thing. You see, lithium is marked in blue, and it forms layers along the C direction of the unit cell. The layers are connected through chromium-nitrogen units, which marked in red. On the right, you can see different layers, and you can see how complex are they. I'm not going to talk about how these layers are constructed, but you can see that it's extremely complex thing. So, why this compound is so important? Here we have both chromium 4 and chromium 5 in the structure, which might be beneficial for batteries because of different oxidation states. Secondly, we saw high lithium content. It was lithium 14. So this would be also beneficial, or at least we believe. Lithium have 3 different sites in the structure: trigonal, tetrahedra, and dumbbells. These 3 sites would be beneficial for battery performance. So overall, I showed you only 2 examples in this rich chemistry, which might be used as cathode materials. These compounds possess not only beautiful and complex chemistry as we saw today, but also a great potential to be used in batteries. With that, I would like to thank my group, Michal Leskas, and my previous group in Germany, Yuri Green, and all of you for your attention.